After dealing with a very interesting problem based on the reaction between anisole and succinic anhydride, now let's move on to the next very good looking question where we have to find out the unstable molecule at room temperature, where 4 molecules are given to us. Now, to solve this question, you need to note down 3 classes of cyclic molecules. Remember, these are cyclic molecules. They come under 3 categories. One is aromatic, second one is anti-aromatic, and the third one is non-aromatic. Now let's look into the characteristics of these compounds. First, look at the aromatic compounds. These are cyclic, as I already told you, and they should have planar molecule and complete conjugation, and you should contain 4n plus 2 pi electrons, where n is equal to 1, 2, 3, so on, any integer, and this 4n plus 2 pi electron rule is called as Huckel rule for aromatic compounds. Huckel's rule. Now let's look into the anti-aromatic compounds. This is also a planar molecule, and like aromatic compounds, it is also completely conjugated. But unlike aromatic compounds, it has 4n pi electrons, where n is equal to 1, 2, 3, so on. They can be anything. That is n, positive natural number. Now let's look at the third category, which is non-aromatic compound. A compound is non-aromatic if it is neither aromatic, that is not aromatic, and not anti-aromatic. That is, the characteristics of this would be if the molecules lack planarity, or if they lack complete conjugation, or even they may not have 4n plus 2 pi electrons or 4n pi electrons. And one more interesting fact is that at room temperature, aromatic compounds and non-aromatic compounds are very stable, and in between aromatic compounds and non-aromatic compounds, aromatic compounds are very stable, and anti-aromatic compounds are unstable. The reason behind this is a very complicated one, but for now remember that at room temperature, aromatic compounds and non-aromatic compounds are stable and anti-aromatic compounds are unstable. So let's categorize these given compounds into group of aromatic or anti-aromatic or non-aromatic. The first one given to you is this one, where you have a cyclohexane with 2 bonds. Now, as obvious thing, it is planar. It has 4 pi electrons, 1, 2, 3, 4 pi electrons, but it doesn't have conjugation, complete conjugation. It's obvious because these 2 bonds are in resonance between 1, 2, 3, 4, these carbons, but these carbons are not involved in resonance. If you draw the resonating structures for it, or delocalized structures, you will have, say, positive charge here, negative charge here once, or you can even have negative charge here and positive charge here, but see that these two carbons are not involved in this lines. So because of this, it is non-aromatic compound and it is stable at room temperature. Now let's look into the second compound where you have cyclobutadiene. This is cyclobutadiene. Now obvious thing, it is planar and it has 4 pi electrons, 1, 2, 3, 4, and it also has complete conjugation. I'll show you the structures now. This bond shifting this direction and this shifting this direction. You will get this one. So here it satisfies the condition for anti-aromatic compounds where n is equal to 1, that is 4n, n equal to 1, and so it is anti-aromatic compound and it is unstable at room temperature. Now let's look into the third part where you have this compound, this one, 2 double bonds and a double bond O. Now it is planar, and just by looking at it one may think that there is no conjugation in it because this carbon atom appears to lack conjugation. But the thing is that C double bond O is polar molecule and it exists as O minus C plus. So the structure for it will be of form O minus here plus here. Now you can see now this has complete conjugation. I'll show you the structures now. And also it has 4 pi electrons, 1, 2, 3, 4, 4 pi electrons and complete conjugation. So it obeys the condition for anti-aromatic compounds and so it is unstable. Yeah, the structures for it would be, say this bond has shifted this direction, negative charge here and positive charge here. You have got O minus here, double bond here, and positive charge here, and shift this bond this direction, you get a positive charge here. That is, you will have double bond here, O minus, and this positive charge. As you can see, this positive charge is delocalized over this complete ring, and you can also write this of the form where it shows that 2 double bonds are in conjugation with this positive charge and it's unstable as discussed earlier. Let's look at the fourth compound, this one, where you have 7-membered ring, 1, 2, 3, 4, 5, 6, 7. Let's draw its structure. 1, 2, 3, 4, 5, 6 carbon and 7th carbon here, where you have C double bond O and 3 bonds here. Now just like this compound, it has O minus C plus. I'll draw the structure again. O minus C plus. As you can see, it has planarity and it is contain 1, 2, 3, 4, 5, 6 pi electrons and it is completely conjugated. Try out the conjugated structures for this molecule just like this one. And so as it obeys the condition for aromatic compounds, it is aromatic and stable at room temperature. So among the given compounds, second one and third one are unstable one at room temperature. Now let's quickly recap what we have learned here. We have learned about aromatic compounds, non-aromatic compounds, anti-aromatic compounds. Also note that these three are only for cyclic compounds. We have learned the conditions for it, where you have told that aromatic compounds have 4n plus 2 pi electrons, anti-aromatic have 4n pi electrons, non-aromatic compounds are neither aromatic nor anti-aromatic. And later we have told that C double bond O is polar and it exists as C, O minus and positive charge on carbon. And one more thing is that aromatic compounds and non-aromatic compounds are stable at room temperature, whereas anti-aromatic compounds are unstable. And in between aromatic and non-aromatic, aromatic are more stable than non-aromatic compounds. And so we have concluded that B and C, being anti-aromatic compounds, are unstable at room temperature. Now here we have one more interesting question for you, that is, you have to find if this compound is stable or unstable at room temperature. This 8-membered carbon ring. Now we want to discuss this one because it's a tricky one. It may seem to be planar, it seem to be, and it has, as obvious here, 1, 2, 3, 4, 5, 6, 7, 8 pi electrons, and it appears to be completely conjugated. It appears here, but it is not, and it appears to be anti-aromatic, but it is not. In reality, it is non-aromatic compound, because this 8-membered ring will not exist of this form, and it is observed that it exists in a tub shape like this one. So there is no planarity and no complete conjugation, and so it is a non-aromatic compound and it is stable at room temperature. Now let's move to the next question. After discussing the three types of cyclic compounds, let's move on to the next question, where we have butene treated with a series of reagents to give X, Y and Z, and we are asked to find out what X, Y, Z are. So to solve this question, let's look into the reagent given to us, as we did the same thing for every question, and that is what we have to do in organic chemistry. The reagent given to us is R C double bond O, O star, O18D. Here I want to discuss the importance of this reagent and also some other reagents which does the same work as this reagent do. They are H2SO5. The structure of it is S double bond O, double bond O, OH, O, O, H, and Ag in presence of O2, and also MCPBA. This is metachloro perbenzoic acid. I'll draw the structure for you. You have perbenzoic acid, which is this one. You have paracid bond, that is peroxide, and meta to it you have chlorine. Now the importance of this one is they are used in the formation of epoxides, which is CC, this one. They convert C double bond C to and epoxy. So as you can see, in the first reagent you have three different oxygens. One is simple oxygen and one is O star, maybe it is a radioactive, and next one is an isotope of oxygen, which is O18. And one of these oxygens get attached to it, this C double bond C, and you have to know which of these oxygens get attaches to it. For that you need to know the mechanism of it. Let's look into its mechanism deeply. If you have any C double bond C, say you have a peracid. Now remember that all these are peracids. The common thing is that all these are peroxide bond and meta-chloroperbenzoic acid too, and this too does the same action. Now come back to its mechanism. Let's say you have any peracid like this one, R, C double bond O, O, OH. Let's take the given reagent given to us, which is O star 18. Now the mechanism of it is like this one. C double bond O, R here, you have O star here, and O18 hydrogen here. Now thing is that first this lone pair and this bond are in resonance, that is they can shift in this direction, and you also know that this is a nucleophile, and whenever this donates electrons to it, it gets a positive charge, and this, to counterbalance this charge, takes up this bond, that is both the electrons of this shared pair, and it will give a positive charge here, and this nucleophile which you have gives its electrons to it also. Then you will get a positive charge here on this carbon, and you know that oxygen has lone pair of electrons. This oxygen gives its electrons to it. Also here you will be getting a negative charge on this oxygen, and this takes this hydrogen. Finally you are going to get O18, this one, and here you have OH, R double bond O star. So this is the mechanism for first part, and the alkene given to us is butene. So you have this one as your X is equal to C, you have O18 here. Now let's come to the second part, where you have subsequently treated this with pH NGBr, where you have phenyl ring pH, and this is Grignard reagent RMgX. It provides R minus, and here pH minus, a negative charge here. This R minus can either act as a base or nucleophile. Now if there exists any acidic hydrogen, this is a symbol for there exists, as you have studied in your mathematics, and if there is no acidic hydrogen, and if there is electrophilic site, it acts as nucleophile. Now in this one, that is X, you do not have electrophilic, that is acidic hydrogen, but you know that this is very unstable, this epoxide bond. If you take this, because we have already discussed this one, that oxygen is sp3 hybridized and the bond angle here is 60 degrees, and for sp3 it should be 109 degrees 28 minutes. So there is a lot of deviation, about 49 degrees 28 minutes, which is a lot of angle strain. So this is unstable. This part we have already discussed before. And so this R minus attacks this epoxide bond, can attack either from this side or from this side to give a cleaved product, that is this bond shifting this direction or this direction. Now see which happens. This is basically a substitution reaction, that is it's typically like a substitution because it's just like substituting this bond or this bond, that is this approaching bond is substituting this one. Now see, if it attacks from this side, the R minus, it suffers steric hindrance or steric repulsions from this ethyl group and the hydrogen. Of course the hydrogen effect is negligible, but substitution requires a sterically free side, and this is sterically free. And we have already discussed this part. So R minus won't attack from this side, that is R minus won't attack on this side, but it will attack on this side. And now when it attacks on this side, this bond cleaves away and you will get CCC, O minus here, carbon here and R here. Now in the given problem, R for us is pH. This R is pH. So what you are finally going to obtain is CCC O minus C pH. And the last one which we have done is subjected this one to H3O plus, that is hyd. You have given H plus to this. When you add H plus, this O minus gets protonated and you are going to get CCC OH C pH. Now this is your final Z and this is your Y. Also, interesting thing is that it's a previous IT question, and see how logically it was asked and how logically it was framed. It was meant for you to know the mechanism how this peroxide, which is RC double bond O O D, attacks on this C double bond C to give an epoxide. It contains a peroxide bond and it's a peracid. So in the summary of it, we shall see that how this attacks on this to give a epoxide, and we have seen that RMGX reaction, and we have also seen that it attacks on sterically free side, which is this side, and if it attacks from this side, we have told that it will suffer steric repulsions. And finally on we have added H3O plus, that is on hydration in acidic medium. You have got OH as your final product. Now with this we are done with this question. Let's move to the next question.